Hello, students. We are basically done with Unit 6. So I'm going to show you a couple of things. Today is the practice that's on your schedule. The 18th is when I'm making this video. So depending on when you're watching this is where you can find a critical piece of information that I'll show you. And then I'll give you an optional piece of information that I strongly feel like we should spend our time learning to read and use, because I believe technology is in the future, but just in case, I'm going to show you both. So in the On Your Own, you will see this link, standard normal table with negative and positive z-scores. You're going to click it, it's going to download, boop, you'll open it up. Okay, so find where that downloads, and this is what it looks like. Hey, the standard normal table. This is also a chart in the back of your book. We'll talk about today what this means, how we use it, and then we're going to solve some practice problems and go straight into the quiz. So we're going to use both this table and the technology that I like. I think it's good. I think we should use it. I do believe these tables are going away. Okay, so a couple of things I'll show you right now. So we're going to do this first, question number 8, using the technology. And then we'll jump to the quiz, because I'll use the quiz to explore and explain how to use z-tables and what they mean. Hopefully it starts to make sense to you. If not, please watch today's recording as we use a Plinko machine and look at the probabilities of where the balls land and how it relates to the standard normal curve. So, okay. Here we have the length of newborn girls. They're normally distributed with a mean of 49.2 centimeters and a standard deviation of 1.8 centimeters. What percent of newborn girls will be 45 centimeters or shorter? So if we were to do this using the table of values that is right there, you're going to need to find the z-score, because that's what the table of values refers to. Then you're going to find 45, right? The raw data, 45 is what they're asking us, minus the mean, 49.2, all of that over 1.8. Use a calculator, 45 minus 49.2 divided by 1.8 gives you a z-score of negative 2.33. Okay, so then we'll go to our table of values. We'll look for that z-score, and that will give us whatever is inside the table of values, the percent of newborn girls that will be 45 centimeters or shorter. And again, that's because the table of values gives you a cumulative from the left probability. If that doesn't make sense, that's okay. Just know that's how you read the table. It gives you the probability for the area under the curve, starting from the left, filling up towards that z-score towards the right. So some questions ask you for the greater than, this area over here, but your table of values will give you all of this area. So to find this area, you'll have to do 1 minus that area, and it will give you this leftover area. So be careful, be creative, looking at where you want the probability to be, whether it's greater than, less than, or maybe sometimes in between. You're going to have to figure out what values you add, subtract, okay? And I can help you with that. All right, so we have that negative 2.33. So you have your table. How you read this? The first 2 digits for your table are on the left. The third digit is the columns. So you have the rows, which are the first 2 digits, the number in front of the decimal, and the first decimal place, the 10th place. And the columns represent the 100th place. So we needed negative 2.33. So 0, 1, 2, 3, right there. So there it is, our table of values. That is the probability that a newborn baby girl will be shorter than 45 centimeters. So they're asking for the percent chance. Percent is per 100, so we have to convert that. Be careful as you convert that, right? That's not 99%. That's not even 9.9%. That's 0.99%. Okay? Boop, boop. All right, check answer. However, the technology that we're going to be using, which I can't believe I got rid of. There we go. I give you guys that link, so if you want that link, just let me know. Well, we're going to use the information that we were given, and we're going to use it up here because they give you the raw score. The raw score, okay? So we're going to do 45, 49.2, and 1.8. 45 is the raw score. The population mean is 49.2, and the standard deviation is 1.8. So that's where that data goes into our calculator. They're basically going to use the same formula, only they're going to do it for us. Cool. So there it is. See, there's the formula. The raw data point minus the mean divided by the standard deviation. Boom. Aha. So then they give us what we're looking for, p-value from a z-table. So the value, this is it right here. So notice it's 9.8. So this table is a little bit more precise than our table of values, but you would get the wrong answer if we came back over here and we wrote 9.8. Check. Oh, it's wrong. Check. Oh, it's wrong. And then look, it tells you, okay, you were very close. So if that happens, that's because this is actually more accurate than the table of values, as the table of values is rounded. Okay, cool. So that's it. And then look, that's the probability. There's the area under the graph that a newborn girl, baby girl, would be born, and she is less than 45 centimeters. Right there, that little tiny bit of probability. Okay, a couple of things just to extend your thinking. That's the math, that's the what, that's the why. But statistics really relies on the context of the situation. So are we talking about full term, the average full term baby girl born in the United States, right? That's a very specific group that we're making this projection for. You have less than a 1% chance, if you're full term, if you're born in the United States, that you will have a baby shorter than 45 centimeters. But if we're looking at maybe other countries or not full term babies, and we have a lot of questions here. Does this include premature babies? Is this every baby? Is it every baby in the world? Every baby in the United States? So all of those big ideas come into play when you're looking at the statistics and the probabilities. So you need all of that information to make an accurate conclusion. Here they're just giving you numbers about some population of babies where the average height is 49.2 centimeters with a standard deviation of 1.8 centimeters. Newborn girls. That's it. We don't know where they're getting that population or numbers from. They're not giving us any further information. So we would just say, hey, according to our data, about 1% of babies will be 45 centimeters or shorter. I don't know if that makes sense, but it's important to ask those questions as you leave the classroom, because most of information is not going to be a word problem in a math book. It's going to be about the world around you, and you need to take into consideration everything you know about the data and the information you're being presented. Now, all right, so that's the basic gist of it. We're going to go use the quiz now to look at the z-score calculator and the table of charts. It's not due till tomorrow, depending on whenever you watch this video. Aha, okay. Using technology or a z-score table, answer the question. This expression, probability that z is less than 1.87, represents the area under the standard normal curve below a given value of z. What is that probability? Great. So in our calculator, boop, zoom out, scroll down. Was it negative? I already forgot. Regular, 1.87. Doesn't matter. There's your z-score. You just put it in there, 1.87. Where it says z-score, z equals that, hit calculate. Aha. And then now they give you the less than, the greater than, the in between 0 and that, between the negative z and positive z, or the tail values, right? So that's what all of this information is. So that comes in handy later on as you start to ask different questions about your data. But for now, they just want this one, less than. So 969, rounded to fourth, 3, 9693. Aha, 9693. Okay, let's do the same thing in a table of values. Table of values, it works for the z less than. It has the cumulative property starting from the left up. So when it says less than, you're done. You just go read the table. 1.87, so we go down to positive 1.8, keep scrolling. 1.8, 0, 1, 2, 3, 4, 5, 6, 7. Aha, there it is. That means whatever this represents, you have a very good likelihood that you'll be that score or smaller. So a 97% chance that whatever that's referring to is you'll be either that as high or lower. You'll be that amount or lower. Okay, that's question 1, whether you use the calculator or your table. Question 2. All right, so this is a story problem about Jill. Jill has picked 276 huckleberries in this contest. So it's normally distributed, though, with a mean of 300. Average berries picked is 300 and a standard deviation of 53, meaning the data varies in between each person's by the standard amount of 53. We would expect a 53 difference. That's just letting you know how spread out your data is. Does that make sense? That means there's some really, it's kind of pulling your data away from the mean by 53 huckleberries. Some people picked 53 more and quantities, chunks of 53, right? Standard deviations of 53. And some people picked 53 less, chunking it down. Okay, that's just what it means. So what percent of huckleberry pickers picked less than Jill? So again, if you're going to use this table of values, you need to convert that to a z-score. And since it's the z-score of less, you just have to read the table perfectly. Just go find it. So we're actually going to use the technology. Mean is 300. Standard deviation is 53. The raw score is Jill's. It's 276. So we're going to scroll back up. The raw score is 276. The population mean was 300. And the standard deviation was 53. So here we go. It's going to give you your z-score, so you can go use the z-table. Here's your z-score. Negative, there's the calculations that I would do in a calculator. Negative 0.45. That's only going to go to 5. It's not going to finish that. So we'll go look at our table, and then we'll go look up here to see if we get the same thing. So 0.45, negative 0.45. We go to my table. Negative 0, 0.401, 2, 3, 4, 5, 32.64. So as a percent, that's 33%, about 32.6%. That's how many people picked less than Jill, because that's what it means. The probability is a percentage. It's a proportion of the area under the curve. So let's go do that in the table. Look, 32.5%, right? So 33, if we round it, 33%. And then there's the visual. That's all of the possible people who picked different berry amounts that were less than Jill. So just about a third of the people will pick less than Jill, or about the same amount, 33%. Does that make sense what's happening, what the normal curve is saying, and how we read the normal curve? Hopefully the story problems are starting to come together as to why this is pretty powerful. And especially if you ask better questions, and they can lead to more questions. All right, question 3. Using technology or the z-score table. All right, here we go. The odometer on a random sample of identical model sports cars, wow, are normally distributed with a mean of 120,000 miles and a standard deviation of 30,000 miles. Consider a group of 6,000 sports cars. So now we're going to think of this group of 6,000. We gathered a bunch of sports cars, same identical ones. Approximately how many sports cars will have less than 150,000 miles? So again, it's still less than. They're being very nice to you because the table values is cumulative up to the z-score. So the less than questions are straightforward. It's just whatever that probability is in that table, that's your percent. And then once you have your percent of cars, you just multiply it by your sample, what they're asking you to estimate. You can then estimate how many cars out of 6,000 will have 150,000 miles or less. So let's use this table, the calculator. And if you want to use the table of values, I'll again show you where the z-score is on this calculator, remind you how to find it by hand, and then you can go ahead and do that this way. So we have 150 is our value, 120 is our mean, and 30 is our standard deviation. 150,000, 120, and 30. Hey, it's like I've done this before. Okay, so again, we have our, the z-score is exactly 1. I didn't notice that. That's crazy. So that's the z-score from the table. So you could go look up one standard deviation, right? So if you have, I don't know if that makes sense to you, but okay, anyway, it's 1 standard deviation above the mean. So we know there's going to be 50% because up to the mean is 50%, right? Up to that center line is half our data. Half our data is on the left, half our data is on the right when we look at a normal curve. Then we remember we have that 68, 95, 97 rule. But if you remember, it also broke it down into 34% and 34% below the mean, 1 standard deviation above the mean. So it makes sense that 34 plus 50 is 84% of our cars are going to be less than 150,000 miles. Okay, we're not done though. So that's the number. This whole number, we can use that to be more precise, is the probability of finding a sports car in your 6,000 cars that has 150,000 miles or less. We'll come back here. They give you a calculator. So that's what you're going to use this for. Okay. Remember, it's 6,000 sports cars is what we're checking. So we're going to multiply that by the probability that we'll find that. So 84134, 0.84134. We're then going to hit equals. Ta-da! So we now know that because of that decimal, 5,048 cars of that group of 6,000 cars, that's the probability, or that's how many cars we would expect when we went in and checked them, that they would have 150,000 miles or less. Does that make sense? What the inside value in the story, how it works in these different contexts, and why that's kind of helpful to know, like, whoa, if we get a bunch of cars, like way more than we would expect, that are either also like below, like 100% or below, we might want to check our data, right? It leads to further questions, these observations and the statistics with the probabilities under the normal curve. Maybe not, maybe it doesn't, and that's okay. Cool. So we have a z-score. What is the z-score? But this time they're asking you for the read inside the chart. So there's the 1.27. So let's look at the chart. To go backwards, you're looking for that right there. It's already right there. That's funny. 0.1271. Do you see it? So now you go inside the chart. If they're asking you to find the z-score, you look for the number they're asking inside the chart, and then you go backwards. So negative 1.4, right? How to use technology. Zoom out. Let's clear. Let's keep scrolling down. Clear. Aha. Remember, it's always going to lead cumulatively. So you're going to want to put it right there. So here we go. There it is. It's already stored data. Aha. And there it is. It's the same z-score that we found in the table of values. You just have to be careful. You have to put it in the right location in the calculator to spit out the correct z-score. Because if we put this in this one and delete it, it's going to flip it. It's going to have the area over here be equal to that. See, this red is going to flip over to there. Or sorry, this right here will be this amount. These two will switch places. This red will be filled in this way. This amount of red will be filled in this way. But it'll give you a different z-score. See, it flip-flopped. Hey, look at that. It gave you the positive z-score. Okay. Anyway, just think about those relationships. It's a very powerful tool. So negative 1.14, whether you use your table of values or you use your calculator. Sorry. It's just allergies. It's heavy allergy season here in Yuma in April. Okay. No, I want nope. I want this one, homeowners, because I think it leads to a very good question. So using technology or the Z distribution table to find the indicated area, suppose the ages of people who own their homes are normally distributed with a mean of 42 years and a standard deviation of 3.2 years. Approximately 75% of the homeowners are older than what age? So this is a problem-solving one. They've now flipped it on you. So far they've been kind and just been like less than, less than, less than. Okay, so the chart, the table of values, the probabilities are already built to answer your less than questions, right? You find your z-score and they fill in your data to the left. Therefore, that's the probability that whatever it is you're talking about is less than that z-score. Make sense? But now they've flipped it on you. So you could use this, and I'll show you what to do. Approximately 75% of homeowners are older than what age? Well, you could find inside your table 75%. You could find that z-score, right? And then you'll do, oh no, that actually works. No, it's backwards. It's still backwards, right? Because that z-score is backwards, so that this won't work. Sorry. Ignore me. You need this. So draw your picture correctly. You want 75% to now be shaded over here. Does that make sense? So you need 75% of your area over here. So what area does that leave over here? And then you can use that to find your z-score. So we'll do that method in a second. But first, we're going to use the z-score calculator technology, using technology, okay? But anyway, think about that. Once you figure out what this is, you use that inside inside the table, right? You look for that number inside, then you scroll to the outside to find your z-score. All right, but over here, let's see again, we have 42, 3.2, and 75%. So first we need this. Oh, this is all we're going to do. We're not going to use any of this just yet. So to use technology, we know 75% older. So we're going to go here. That's the percentages inside. We're going to now make that X older 0.75. Calculate. That will give us our z-score. There's our z-score. Look how this is more precise. It's to a third decimal place. Your table of values will only give you to 2 decimal places. Got it? So that is, again, the z-score for the area greater than it would be 75%. But notice it also tells you the area less than, which is what you need to use your table of values. We're looking for 0.25. So go into your table of values, and we're starting to look. Here's 2, 2, 3, 2, right? See, 2, 5, 2, 5, 4. All right. We're taught different strategies in college, but for the purpose of this course, this should be good enough. That's close enough to 25%, so it's negative 0.67. Same thing we found using the z-score here. Okay, so we need that information because we're not done. They want to know what age. That goes back to the raw score. So the raw score is going to be equal to the mean plus the z-score times the standard deviation. So our mean is 42 years for this group. The z-score was negative 0.674 times 3.2. All right, there's no calculator on this one. You could use another calculator. You could use your own calculator. You could use your phone. We're going to do 42. If you use your iPhone, you need to do this part first and then add 42. So let's pretend. We'll do negative 0.674 times 3.2 plus 42. We get 39.8 years old. So we can expect that 75% of the homeowners are older than 39.8 years old. That's older than me. I know, surprising, but it's currently older than me when I'm making this video. I'm only 37. So that's wild to me. What does that mean to you? Age of homeowners. That's a pretty big statistic. All right. Anyway, that's how you answer it. 39.9. Okay, it's close. So say instead of using that 4, you just use 7. I don't know how they got that. Okay, yeah, they just rounded again. So they round and they get you close to 39, but you could see that you got 39.8, so that's clearly the logical answer. All right, so hopefully this video helped you not only use technology and, to me, the antiquated table, z-score table, but understand what's going on under the normal curve. Obviously, our class with the Plinko and the videos I provided is going to give you a better understanding, I hope, about how the probabilities work and why we can use that to determine the probabilities in the tails and the center, given different information, how tall we expect a baby, how old we expect our homeowners. I'd like for you guys to think about this. The average age of homeowners in US. Okay, in 2022, the average age of first-time homebuyers was 36. It's pretty high. This is up from 33 just 1 year prior in 2021. 26% of home buyers were first-time buyers, and so there's a lot of information that is important that you guys can think about as you look at the different ages, right? Look, in your early 30s, lots of people, and now in 2019, wow. All right, anyway, why? Why is that happening? What's happening? How do we change it, slow it down? Because that's really important. We should try to make homes affordable for everybody, but how do we do that? I don't know. What's causing it? I don't know. Those are questions that you would need to do further investigation to ask, but that's the power of statistics. It gives you good observations or good data to where you can look at it and be like, what's going on? That doesn't make sense because I don't expect that. Or I don't like that statistic, I don't like that outcome. How do we change it, right? How do we change the rising age of home ownership? Those are questions for you guys to answer. My job is to help you find these calculations, answer your quiz questions right, teach you all those different skills, and then you guys learn that critical thinking and apply it to the future. Thank you guys for watching, and I'll see you guys in class.